All right, so now we're continuing on with number 17. It says a car is moving with a speed of 32 meters per second. The driver sees an accident ahead and slams on the brakes, giving the car a deceleration of 3.5 meters per second squared. How far does the car travel after the driver put on the brake and before it comes to a stop? So we want to know the distance. This sounds an awful lot like a kinematics problem, and that is in fact what it is. So this is all about motion like we did at the beginning of the class. And so we're going to jump into motion here and see what we can do. In this case, we are given the initial and final velocities. We're given the acceleration, and we're asked to find distance. So the thing we don't care about is time. So I'm going to pick the kinematics equation that does not involve time. And that's the one that looks like v squared equals v initial squared plus 2a times the quantity x minus x naught. So that's going to be the equation I plug into. In this case, my final velocity is 0. My initial velocity is 32. And then I have 2 times the acceleration. It tells us that we decelerate at a rate of 3.5. So decelerate means in the opposite direction so that it slows us down. So that's going to be a negative 3.5. And then we're going to multiply by our final position, which is what we're trying to find, minus our initial position, which I'm going to call 0. And so we just want to go through now and solve this equation for x. So let me grab my calculator. So 32 squared divided by, it looks like 7. So that gives me 146.3. And that is answer D. Again, if you have any questions, just let me know. Stop me while I'm on that problem before I go on to the next one.
On that one, I
Yes.
actually got a different answer from you. I got 4.57. And so I'm
Okay.
wondering what I did. Oh, I didn't square it. That makes sense.
There you go. I'm like, if you use the same equation, we should be getting the same answer. Okay. So math errors happen. So, and 4.6 unfortunately was one of the answers too, which is always a trick thing there. You gotta be like, oh,
Yeah.
yeah. So I think I mentioned this in class, but sometimes these are set up so that the other answers are answers that match up with common mistakes students might make. So you've got to be careful for that. Just because your answer is there does not imply that your answer is correct.
Mhm.
All right, let's look at the next one, number 18. A person throws a ball horizontally from the top of the building that is 22 meters above ground level. The ball lands 100 meters downrange from the base of the building. What is the initial velocity of the ball? So this again sounds like a kinematics problem, but this one is a two-dimensional kinematics problem. So since it's a little more complex, let me just make a list of what it is I know and what it is I don't know. So for this one, I know that my x initial I'm going to call 0, and my y initial is going to be 22 meters. My x final is going to be, where is it? 100 meters. And my y final is going to be 0. My velocity initial in the x direction is what I'm trying to find. That's my unknown. And my v initial in the y direction is 0 because it's being thrown horizontally. And remember, if it's thrown horizontally, it means that it's not being thrown up or down. Final velocities, I don't know anything about. Acceleration in the x direction is 0, and acceleration in the y direction is minus 9.8. And then time, I don't know anything about. All right, so as I look at these two columns, I'm like, okay, I know more about my y column than I do about my x. What can I solve for in my y column that's going to help me solve my x? And the answer to that is time. So I'm going to put a question mark here on my time. And that's going to be the first thing I try to solve. That means that I don't care about final velocity. So the equation I'm going to use here is that y equals y initial plus v initial t plus 1/2 a t squared. That's going to be my starting equation. That gives me 0 equals 22 plus 0 minus 4.9 times t squared, and that will allow me to solve for t. So when I plug that into my calculator, I get divided by 4.9. Oops. Yep. And then the square root of that answer. and I get 2.12 seconds. Now that I know that time, I look over at my x column and I say, well, the thing I don't care about in my x column is the final velocity, so I'm going to use the same equation in the x direction now. But this time I'm going to plug in my x values. So 100 is equal to 0 plus v naught times 2.12 plus 0, because there's no acceleration there. And I'm going to use that equation to solve for v naught. And when I do that, I get 47.17. 47.17 meters per second. And that most closely resembles answer D. All right. Number 19. Delaney's Mini Cooper runs out of gas as she's driving up a long hill. She lets the car roll without putting on the brakes. As it slows down, stops, and then starts rolling backwards, its velocity up the hill is given by the equation v equals 60 minus 2t, where the velocity is measured in feet per second and t is the number of seconds since her car runs out of gas. What is the total distance her car rolls between t equals 10 and t equals 40 seconds? So if we know the velocity as a function of time, how do we find the distance? So first of all, this velocity does change with time, but it is linear with time, which means this is actually a kinematic motion. So we do have the choice at this point of either using kinematics or using direct integration to find our answer. It doesn't really matter which one you choose. If you want to set it up as a kinematics problem, you'd read that v equals 60 minus 2t as v equals v naught plus at. So they're telling you your v naught is 60. They're telling you your acceleration is -2, and you can set it up and solve it that way. If, on the other hand, you want to do it through direct integration, that would work whether or not you have a t squared term or a t cubed term. It's the more general approach. And since they've given it as a function of time here, let's go ahead and practice by using that. So if we know the velocity as a function of time, how would you find the displacement? Well, the displacement is just going to be the integral of v times dt. So we're going to just integrate that velocity function to find the position function. Now in this case, when we do that, when we start with the 60, when we integrate the 60, we get 60t. And then when we integrate the minus 2t, that's going to give us minus 2t squared over 2, which just gives us minus t squared. So that is our equation for the position as a function of time. Now we want to know the distance between time equals 10 and time equals 40. So x at time equals 10, we're just going to plug in 10 and see what we get. So we're going to have 60 times 10 minus 10 squared. So that's 600 minus 100, which is 500. And our x at 40, t equals 40, is going to give us something like 60 times 40 minus 40 squared. So that's 2400 minus 1600. So that looks like what? It looks like 800. Did I do that right?
Yeah, I was thinking 300, but I did it in my head, so I could be wrong.
You got 300 for the 40 seconds or for the total displacement?
Oh, for the total displacement.
Right, so I'm agreeing with you, which is not the answer I had written down as what I had on the answer key. So let's take a look at it. So that means our delta x, which is our displacement, is going to be our final minus our initial, which is, as we both said, 300 feet. So let's see, is that one of the answers? It is one of the answers, but it is answer B. I had down that that was not the right answer. Let's see if I still have that. Do I have an answer key up over on the side here? Yeah, so that might be a mistake in the answer key. So we get answer B there, not answer D. So keep an eye on that. Mistakes happen. Okay. So answer B, not answer D. Why don't we check that by doing it the kinematics method just to see? So we said that using the kinematics method, our V naught would be equal to 60. Our acceleration would be -2. We know that we're going to try and find our position using x initial. We'll just call x initial being, actually no, we'll just use x initial. Yeah, let's just find the delta x. And then we know that the total time, yeah, I'm going to do it as 2 steps. So I'm going to use x initial as 0, and I want to find the x final. Oops. Both at time equals 10, and then again at time equals 40. So again, I don't care about the final velocity, so this is going to be the x equals x naught plus v naught t plus 1/2 a t. Can I fit it? Squared. Yes, just barely got it in. So for the time equals 10, I'm going to get 0 plus 60 times 10 plus -1 times 10 squared. So that looks like the same as we got before. That gives us about, oh wait, sign error. That should be a minus there. I can't go back and change it now. So that plus should be a minus in there. So that should give us the x equals 500 we got before. Let me check that one more time, make sure that's not our error. So 1/2 times our acceleration, which is negative. Yep, 500, I agree. And then let's do it again for time equals 40. So if we do it for time equals 40, we get x equals 0 plus 60 times 40. It's coming out exactly the same. And then minus 1/2 times 2, which is 1 times 40 squared. Yeah, it looks like that was just a mistake in the answer key, and that should be 300 feet. Oops, that one should be 800, sorry. And then the delta x. Minus 500, which is 300. Okay, so it looks like the answer to that one is correctly B, not the answer that was in the answer key, which was D. So be aware of that. I will update that for future use. In fact, I'll update that right now. Number 19 should be B. Okay. All right. Hopefully our only mistake, but we'll find out as we go. All right, let's look at 20. An object is being acted upon by 3 forces and moves with a constant velocity. So as soon as you see constant velocity there, that tells you that your net force is 0. You have 0 acceleration. One force is 60 newtons along the x-axis. The other is 75 newtons along the y-axis. What is the magnitude of the third force? So if I were to draw a force diagram for this object, we have 3 forces acting on it, and we know that overall it's in equilibrium. So if I've got a little box here, we've got a force in this direction. Oops. Shoot. My bad. Get that out. Yes, okay. We've got a force in this direction. And then the other force is going to have to be out in that direction in order for them to balance. And we know that this one is 60, and this one up here is 75. And we want to know what is the value over here. Okay? So in terms of the x direction, we're going to have the sum of the forces is going to be 60 plus 0 for the 75 Newton one, plus the force in the x direction for the third one. Do I have my caps lock on? Yep, I do. All right. And together they have to be equal to 0, which tells us that the force component in the x direction for that third force is going to be -60. And if we do our forces in the y direction, we get 0 plus 75 plus the y component force has to equal 0. And that tells us that the y component force is equal to -75. Now, you might have jumped there already and didn't have to write that all out to get there. But what that does tell you is that the magnitude of your force is going to be the square root of 60 squared plus 75 squared. And when I plug that into my calculator, I get 4,500. Oh, did I do my square root? Yeah, that doesn't seem right. Let me check that again. Something's not right there. 60 squared plus 75 squared. And then the square root of that answer is... Okay, what am I doing wrong? Oh, I'm putting times instead of plus. Twice in a row I did it. Ooh, it's one of those days. Plus 75 squared. That looks better. Square root my answer. And this time I get 96.05. And that seems to make a lot more sense. 96.05 newtons. And that most closely resembles answer D. All right, next up. Problem 21. An object is being acted upon by three forces and moves with a constant velocity. Oh, look, it's the same exact question, but this time it's just asking what is the direction of the third force. So this time we're just trying to find the angle. So again, we know the x and y components because we found them up here in question number 20. So to find the direction, we want to find theta. And theta is going to be the inverse tangent of the y component over the x component. So that's negative 75 divided by negative 60. And when I put that into my calculator, 60 arc tangent, that gives me 51.3 degrees. Now that, remember, doesn't tell me which quadrant it's in. So then I look at my components and I say, well, my x component is negative and my y component is negative. Or I look at my drawing and say, I've already decided it's in that third quadrant. So to make this into the third quadrant, I need to add 180 degrees to it. So adding 180 to this value gives me 231 degrees, which would be the standard notation. And that is answer C. All right, number 22. All right, a 40-kilogram suitcase is being pulled along the ground by the means of a strap, which exerts a 10 Newton force at an angle 47 degrees above the horizontal. What is the normal force acting on the ground? Acting due to the ground. So here's our suitcase. And we have a pulling force that is pulling it up and to the right, let's call it, at an angle of 47 degrees. And that pulling force is a 10 Newton force. Now, what other forces do we have acting on this? Well, we still have a gravitational force pulling us down, and we have a normal force pushing us up. So let's label those as force normal and mg. And we may or may not have friction, but that's in the x direction, and it turns out not to matter for this problem. To find the normal force, we need to do the sum of our forces in the y direction. And in the y direction, we have the normal force plus the y component of that 10 Newton force. That's going to be 10 times sine of 47 degrees. And then we've got our gravitational force, which is m times g. And together, the sum of our forces in the y direction has to equal 0. From this, we should be able to solve for our normal force. And when I do that, 40 times 9.8 minus 10 sine 47 gives me 384.7. 384.7 newtons. And that most closely resembles answer C. Remember that the normal force is not always equal to mg. And this question was there to find out if by the end of the semester you have learned that. I almost guarantee that you will have one just like this on the exam, where it asks you to find for the normal force. And the normal force is not going to be mg. I'm just going to tell you that now. So be aware that is one of the common misconceptions that people learn in a physics class that we want to make sure you haven't learned. So I will probably have a question, whether it's conceptual or calculation based, that tests whether you have learned that or not.
Okay.
Let's go on with question 23. A 1,000 kilogram car is picking up speed as it goes around a horizontal curve of radius 150. When the speed of the car reaches 30, the car begins to skid sideways. What is the coefficient of static friction between the tires and the road? So while our car is going around in circular motion, the force diagram on our car will have, oh, and that one didn't have an arrow on it, a normal force upward. It will have a gravitational force downward. And it will have a frictional force pulling it towards the center of the circle, whichever direction that happens to be. It's going to be horizontal, either to the left or to the right, depending on which way you drew it. In this case, I've chosen to draw it this way, and that's because I'm assuming that the circular motion that this car is going to be making, although it's a horizontal circle, is going to look something more or less like that circle right there, and the center of the circle is going to be as shown here in the picture. Okay, so now, I should go back and label my forces. So that's a force normal, that's an mg, and that's our frictional force. So that's going to be mu times force normal. Okay, and while the tires are in contact with the ground, that should be a static frictional force. So again, really quickly in the y direction, you're going to get force normal minus mg has to equal 0. So that tells us in this case that the force normal is just equal to mg. And then we have the x direction. And in the x direction, we're going to get mu times the force normal, which we now know is mg, has to equal the mass times the acceleration of the object. In this case, because it's going in circular motion, that acceleration is the centripetal acceleration, v squared over r. Now, you'll notice in this equation that the mass is going to cancel each other out on the left-hand side and on the right-hand side. So you don't have to worry about the masses. The mass of the car is not important here. That mass will just cancel right out. And we want to solve, in this case, for mu. So if we solve for mu, we're going to get that mu is equal to our speed squared, which is 30 squared, divided by r times g. And our r is 150, and g is 9.8. And if I plug that into my calculator, that gives me 0.6122, which most closely resembles answer A. All right. So next is number 24. A force acting on an object moving along the x-axis is given by f of x equals 14x minus 3x squared newtons, where x is in meters. How much work is done by this force as the object moves from x equals -1 to x equals +2? All right, so work is usually force times distance. But when the force is not constant, then we have to use that the work is equal to the integral of the force dotted with the displacement. In this case, dx, because we're going to move in the x direction. So in this case, we're going to get the integral of 14x minus 3x squared dx. I should have had another parentheses in there. Sorry about that. All right, so when we integrate this, the 14x becomes 14x squared divided by 2, so that's 7x squared. And then the minus 3x squared becomes minus 3x cubed divided by 3, which just becomes minus x cubed. Now we still have to evaluate this for our limits. And our limits in this case are -1 to +2. So first, starting with the +2, we're going to get 7 times 2 squared minus 2 cubed. And then we're going to subtract 7 times -1 squared, and then add, oops, that's not an add, oops, let's see if I can go back here, add -1 cubed. Whew. All right, so what does that give us? So 7 times 2 squared, that's 28. 2 cubed is 8, so that's -8. -7 times 1 is -7. And then plus -1 gives us a -1. So I think when I put that all together, that gives me 28 minus 8 is 20 minus another 8 is 12. And that is answer A. All right, number 25. A block of mass m is released from rest at a height r above a horizontal surface. The acceleration due to gravity is g. The block slides along the inside of a frictionless circular hoop of radius r. Which of the following expressions gives the speed of the mass at the bottom of the hoop? So it's released at rest from a height r above a horizontal surface. Okay. All right. So if I draw myself a little circle here, it means that our little box is going to start out at a height r over here, something like that. And then it's going to end up down here at the bottom. I don't know if I can draw another box over here. Nope, it's not going to let me do that. Maybe. So it ends up down here at the bottom. So that's sort of like our before and after. This is a change in height problem, which means that this is going to be related to conservation of energy. Block slides on the inside of a circular loop. I wonder why that's given. Okay, well, let's find out. All right, so at that highest point, at that initial point, it has a potential energy equal to mg times the height, which is r. And it's starting there from rest, so it has no kinetic energy. And then at the end, it has no potential energy, and it's got 1/2 mv squared for its kinetic energy. So the masses cancel out, and we are trying to solve here for v. And so when we solve for v, we get that v squared v squared is going to be equal to 2 times r times g. And that is answer C. Any questions on those so far?
No, so far so good.
All right, I have run out of room on this page, so I'm going to take that as another opportunity to pause our recording.